So hopefully you just watched the lecture on Gauss-Jordan elimination. Gauss-Jordan elimination is really the key to a lot of important problems in linear algebra. So the main point is that we can now take any matrix, regardless of how ugly, put it into the Gauss-Jordan algorithm where we do a systematic procedure of elementary row operations to produce a reduced row echelon form version of the original matrix. So the syntax for accessing the reduced row echelon form of a matrix in Sage is a.rref. So I've predefined some code here to calculate the reduced row echelon form of any matrix. So here I'm defining a matrix A. This is just whatever matrix I was thinking about at the time. And there's two print statements down here. The first print statement will tell us what the matrix is, and the second print statement uses the syntax for reduced row echelon form, a.rref. So if we click evaluate, it should print out whatever the matrix is we're studying. So apparently I was studying a 3 by 4 matrix, and then it'll give us the reduced row echelon form. So here we see we have pivots in the first and third columns, so the rank is 2. And we have non-pivot columns as the second and fourth columns, so the nullity is 2. We can also do this with an augmented matrix. That's our major application. Augmented matrices are used to represent systems. And the idea is that we can take a system that's as complicated as we want, put it into the Gauss-Jordan algorithm, and we get back a reduced row echelon form system, which is much easier to study. So the syntax for this is we define our coefficient matrix A, and then we define the augmentation vector as B here. And then on this fourth line, I'm defining the system with the augmentation syntax. And then the two print statements will print out the augmented matrix, so we can verify that we input the data correctly. And then the second print statement will spit out the reduced row echelon form of the system. So let's click evaluate. Okay, so it looks like I was studying a system that had 3 equations and 4 variables. And keep in mind, the numbers here are like pretty bad. It's not obvious when I look at that system whether or not we have solutions. But the Gauss-Jordan algorithm, which Sage calculated, or which Sage implemented, gives me the reduced row echelon form of this system. And here I can do analysis on the system quite easily. It looks like we have 3 pivots, 1 in the first column, 1 in the second column, but then 1 in the augmented column. So that's telling me that the system is actually inconsistent. There aren't solutions. So here, yet again, we're finding that the Gauss-Jordan algorithm is powerful and useful. One last thing to mention is the concept of rank and nullity are quite important. Remember that the rank of any matrix is the number of pivots in the reduced row echelon form, and the nullity is the number of non-pivot columns in the reduced row echelon form. The syntax for calculating rank is a.rank, open close parentheses, and the syntax for calculating nullity is a.write nullity, open close parentheses. So here I have an example where I just input this terrible matrix. You can ignore this ZZ here. It's not important. So there's 3 print statements. The first print statement will just print out the matrix so we can check whether or not we input the matrix correctly. The second print statement gives me the rank of our matrix. And the third print statement gives me the nullity. So let's click evaluate and see what I was thinking about when I put this in. So here I have a rather large matrix. Let's see, can we count the rows? 1, 2, 3, 4, 5, 6 rows, and 1, 2, 3, 4, 5, 6, 7, 8, and 9 columns. So there's 6 rows and 9 columns. And this is simply telling me that the rank is equal to 4. So if we were to row reduce this matrix, we'd end up with 4 pivot columns. And then it's also telling me that the nullity is 5, which makes sense because the rank plus the nullity always has to equal the number of columns of the matrix. So note here, this is just telling me the rank and the nullity. This isn't giving me the reduced row echelon form. If I wanted to, I could maybe cut this matrix and go back up to my first cell here and paste it in. And if I click evaluate, it should give me that matrix and its reduced row echelon form. Yep. So here we have that terrible matrix I was just looking at. And here's the reduced row echelon form. We see that there are 1, 2, 3, 4 pivots, which confirms that the rank is 4. And then there are 4 non-pivot columns, which tells us that the nullity is, or there are 5 non-pivot columns, so the nullity is 5. So hopefully you find these calculators useful. Enjoy.